Okay, in this example, we're going over the work done by a spring to launch an object. So like a spring-loaded kind of projectile launcher, as it were. And let's set up some of these parameters. We got a spring to launch a 2 kilogram block, and we're going to launch this 2 kilogram block half a meter. So it has its final speed, final launch speed, when the spring is fully compressed or fully extended back to its unstrained length. And so if we're going to impose a coordinate system on here, this will be x, and this right here will be, should be a flat surface, but doesn't look that flat, does it? So this would be coordinate minus 0.50 meters, because we're still going to have x be positive. And so the question is, how do we find the launch velocity using work and energy? And before we do that, I want to see how we might try doing it with forces. Right, as a quick review, the spring force, as we established last time, is equal to minus k delta s, where delta s is the displacement of the string from equilibrium, and it's always against the direction of the displacement. So if you push the spring, it's going to push back, right? If you stretch a rubber band, the force will be towards its original shape. If you blow up a balloon, right? If you blow up a balloon and release and don't tie it up and release it, the balloon, by its stretchiness, will push the air out, right, as it flies everywhere. Those are all examples of elastic restoring forces, of which a spring force is our basic example. And so the thought is we might try to find the launch speed. We should look for the acceleration, right? The idea is that we'll look for the acceleration. And so let's find the spring force in the x direction. Well, the formula, if it's a spring constant of, the spring is a spring constant of 100 newtons per meter. And so the spring force then is in the x direction, would be minus 100 newtons per meter times minus the initial position, or the initial displacement from equilibrium, 0.5 minus 0.5 meters. So you got two minus signs here. You have one from the definition and one from the initial position. So that'll work itself out, obviously, to be plus 50 newtons. All right, so that's the force with which the spring is pushing the block as it's released. And so the thought is that we might try the if we know the force and we assume that it's smooth and we're not going up an incline or anything, we might try finding the acceleration. Right, the acceleration in the x direction is the force over the mass, and so that's 50 newtons divided by 2 kilograms. So that'd be magnitude 25 meters per second squared, right? And so from that we can, once we know the acceleration, let's use one of the kinematic equations of motion, which might be v final squared equals v initial squared plus 2a delta x. All right, the initial speed is 0, and so that v initial squared term gets squashed. And then, so the final speed then is just square root. V final is the square root of 2 times 25 meters per second squared times the displacement magnitude, which is plus 0.5 meters. Right, the displacement of the object is a positive 0.5 meters. The acceleration is also a positive 25, and so that the signs work out in this. And so you look at multiplying these three numbers, and you're always wanting to invoke the associative, well, I was going to say associative and commutative properties of multiplication to make your life easier. That's what they're for. Notice that 2 times 0.5 is 1. And so you got square root of 25. And so you have a speed, launch speed equal to 5.0 meters per second. It doesn't look like we've done anything really new in this example. Here's the issue though. If we perform this experiment in the laboratory, we will find that our launch speed is much more close to 3.5 meters per second. And so we have a predicted launch speed of 5.0 meters per second and a experimental launch speed of 3.5 meters per second. So that is an issue. How are we going to resolve this issue then? Well, we have to look at what we did to solve the problem. So we found the spring force at the very beginning. So that the equation that we used of 100 times 0.5, that is the magnitude of the spring force at the very beginning, right? But as we get, and so the acceleration then, that 25 meters per second, is correctly the acceleration at the very beginning. But here's where Newton's laws come in. I mean, that if it starts from rest, accelerates to the right, it's going to move to the right. But once it moves to the right, the force will decrease, right? Because if you look at the spring force, that equals ma equals spring force or spring constant times displacement. And so the acceleration will decrease, but it's still there. So it keeps speeding up, which causes it to move, but that the change in position then decreases the acceleration, which still speeds it up, which decreases the acceleration further, which still speeds it up, changes position, lowers it even further. And this will continue, process will continue until we've moved to the point where we're actually at the center, the unstrained length of the spring, and there's no force. And if the spring isn't connected to it, then the spring will stay where it's at and the block will shoot off at its speed. So that certainly gives us a acceleration that is not constant. And where the argument breaks down is right here in this arrow, where we're assuming that the acceleration is constant. Because the kinematic equations are only true when you assume that the acceleration is constant. If it's not constant, then the equations are not valid. In fact, we derived them in chapter 2, assuming they were constant. And so we'll have to redo how we're solving this problem. And this is an example where using forces in our simplified way that we've been doing actually breaks down, and now we need to do a problem with work and energy. So I'm going to go ahead and select all of this stuff down here and try to erase it without erasing anything useful. Let's see. I think I got all of it right here, but select it all and delete it. Got most of it. Got a couple of stragglers up there, perhaps. Yeah, a couple things. Okay, I got most of it, but let me just scrub the rest. And then there's stuff at the lower right-hand side, right, that we missed. Okay, hopefully if there's anything else that I missed, I apologize. So let's deal with work and energy now. Okay, we have our equation for the work done by a variable force. In general, forces exerted on objects are highly variable. They change with location. So the work done by the spring force is the integral of the spring force over our specific coordinate, technically ds, s initial to s final. it's helpful in this example to actually work through the minus signs. And so let's, instead of doing it analytically, let's actually do the computation. So what is the integral? Well, it's the integral from minus 0.50 meters, that's the starting point, to 0 meters. What's the equation that we're integrating? You have to be careful when you're integrating this thing, because the formula is, so the force is positive. Okay, so the temptation is to just write kx because you know the force is positive, but x is negative. And so we need the definition of we need Hooke's law. And so it will actually be minus 100x dx. In this expression, or in this limit, x is negative, so it's going to make the term in the parentheses positive. Another way to interpret this that the book must have mentioned is that if you graph the force as a function of position, you'll find that it's a linear, let's see, it's the sign of the force, yeah, it goes like that. And so what we're trying to do is, I guess we're just trying to find the area of this triangle here, aren't we? Right. That yeah, this represents the work done by the spring from minus 0.5 to 0, and it's a positive number, and this has a negative slope. The slope here is minus 100 or minus k in general. So work does have that interpretation as area under the force versus position curve. Good. So moving on with that then, let's plug and chug through the integral. Now this is obviously a very simple integral. This is one of the first ones you learn about. You learn that integrate a constant, you get x, integrate x, you get x squared over 2. So we can pull out the 100, so this is minus 100 x squared over 2, integrated from, or evaluated between, or evaluated at minus 0.5 meters and 0. And when we do that, we certainly have all the correct signs, because we got minus 100 Newton per meter. And on the inside here, we have 0 squared over 2, which is 0, minus negative 0.50 meters squared over 2. The 2 is not squared. That doesn't look good. Let me fix that. Minus 0.50 meters squared over 2. That is the, yeah, that's the calculation. So just a simple remark here, there's 3 minus signs to deal with. And that's something you have to get used to when you're dealing with work and energy. And in fact, when you get to when you get to physics 2, there's another minus sign that often shows up when we're dealing with electric forces and voltages. So the minus sign right in the very front is due to the Hooke's law. The minus sign in the middle is, basic fundamental theorem of calculus, and this minus sign in the parentheses is due to the fact that the spring was, or the mass was on the left side of the origin, right? We defined our typical origin to be to the right and positive, so initial position is negative. All of them cancel, right? Because the negative sign inside the square gets squashed, and the negative outside cancels with the negative inside, and so 0.5 squared is a fourth, divided by 2 is an eighth, so it's 100 over 8 plus 12.5 Newton meters. So that's total work done by the spring, correctly calculated now. And so in this simple problem, we can just take the work done equals the final kinetic energy, since it starts off at rest, and we'll just say K final equals work done by the spring force. And so we got 1/2 mv final squared equals 12.5 plus 12. Oh, no, you don't even need, when dealing with kinetic energy, you don't need a plus or minus because it's always positive. Kinetic energy is a non-negative quantity. And so, and of course, I chose mass to be 2 so that it would cancel with the half. And so this is really like square root of 12.5. Square root of 12.5 is very nearly 35. Or 3.5, sorry. And sure enough, that is the experimental speed that you would find. Different from the one that you had found previously, because the previous way that we did it with just using forces, it's worth a mention real quick here, is that when we assumed that the force was constant, we were finding basically the spring force does work equal to 25 or to 50 Newton meters. The force of 50 newtons, that constant force over the 0.5 meters, which would have given us erroneously a positive 25 Newton meters. And then from that, our speed, as you remember, which is square root 2 times 25 over 2, gave us the 5 meters per second. Okay. Again, that was incorrect at the very beginning. Our assumptions at the very beginning were wrong, assuming that the final speed was constant. Or sorry, assuming that the force was constant. When we assume that the force decreases, we're able to get the correct answer. And these two numbers are related. The erroneous speed versus the actual speed, they're related by a factor of radical 2, because when you do it correctly, when you assume it's constant, you conclude that the spring force does twice as much work as it actually does. It only does half of the work that you incorrectly calculate, and so that's going to make the final speed a factor of radical 2 higher when you assume the force is constant. So that's a good example. Lots of different things on display here. Certainly practice with calculating work of a variable function and actually doing it rather than just doing it theoretically with the formulas. So good practice with negative signs.